Welcome to pre-built JOP Chains with the JOP ROCKET, bypassing DEP without ROP. Hi, I'm Dr. Brizendine, and I'm the director of the Verona Lab. I'm also the creator of the JOP ROCKET. I dabble in being an assistant professor of computer and cyber sciences at Dakota State University. My interests include software exploitation, reverse engineering, code reuse attacks, malware analysis, and just generally offensive security. I'm joined by my co-speaker, Austin Babcock, who is a graduate student at Dakota State University, where he studies cyber operations and computer science. Austin is a security researcher at Verona Lab at Dakota State, where he works with me to develop a new shellcode analysis framework funded by an NSA grant. He is a contributor to the JOP ROCKET, and so skilled is he at jump-oriented programming, you could call him a JOP whisperer. His interests include software exploitation, fuzzing, hey, he built his own fuzzer, reverse engineering, and bug bounties. So what are we going to talk about today? Well, we'll provide a background into jump-oriented programming. We'll introduce the JOP ROCKET. We'll have a manual approach to jump-oriented programming, automated JOP chain generation, and we'll provide demos for both of those. We'll touch on advanced topics like switching registers for dispatcher gadgets and functional gadgets, control flow guard, ASLR and JOP, and using JOP as another form of ROP. So let's dig into that background. Did we create jump-oriented programming? Let me think. No, actually, we didn't. It's been around for about a decade, but the academic literature is very, very sparse, minimal. Some serious limitations. For one, there's no real dedicated tool to facilitate JOP gadget discovery before the JOP ROCKET. And more to the point, no actual documentation on how to actually do JOP in a real-world Windows environment. More questions than answers, which we resolved. So lots of minute details that we had to figure out for this to even work. We introduced the JOP ROCKET at DEF CON 27, but now at Black Hat Asia, we introduce a refinement, a novel technique to build a complete JOP chain to bypass DEP purely through automation. So control flow with JOP, no returns, no stack. We don't use them for control flow. Instead, we're going to use the jump and call instructions. Still, we will also use the stack, but only for when API calls. Pure JOP will use a dispatcher gadget and dispatch table as the means to direct control flow. Another style is the bring your own pop jump, which is effectively ROP without the rets. And we'll talk about that later on. So let's see JOP control flow in action. We have a dispatcher, and that will take us to a dispatch table, which contains addresses for functional gadgets, and those go back to the dispatcher. Okay, so dispatcher goes to an address. He dereferences it, does the move EBX, and then right on back to the dispatcher. We advance forward 4 to our next address, dereference, do that, and then back to the dispatcher. And then this just simply repeats for however many gadgets that we have. So the key elements here for jump-oriented programming are dispatch table. This contains the entries for all of our functional gadgets, all of their addresses. Typically, we'll put this on the heap, although we can also do the .data section or the stack, and we'll separate these with uniform padding. The dispatcher gadget allows us to move in a predictable fashion, forwards, backwards, however you want to do it, as long as it's predictable. Functional gadgets, we can think of these as more similar to our traditional ROP gadgets, except they're going to terminate in a jump or a call. Yeah, we can do calls on over to the register that takes us back to the dispatcher gadget. And then Windows APIs. Of course, we'll use these to do things like bypass DEP. And with that, we'll let Austin talk next.
So we'll take another look at our JOP control flow here. We have a diagram similar to before, however, maybe a little bit more in-depth. We have our dispatcher gadget on the left. We we have our dispatch table in the middle, and we have our functional gadgets on the right. So our dispatcher gadget is using EDI to store the address of our dispatch table. That jump dereference EDI is going to bring us to a functional gadget based on what is in our dispatch table. So our functional gadget will end in a jump EDX in this example because EDX is holding the address of our dispatcher gadget. Once we return back around to our dispatcher gadget, that will increment our EDI register, our dispatch tables pointer, and bring us to the next functional gadget in the list. So that's how our control flow for JOP works. We keep on going around in this loop, and you might notice that ESP is not a part of this control flow at all. So this is a bit different from ROP, where our entire control flow is based on the stack. So we're supplying all of our pointers in a row on the stack with ROP, and then that return at the end of each gadget is kind of the glue tying them all together. With JOP, on the other hand, the stack still does play a role. However, it looks different because our control flow isn't tied to the stack at all. So with JOP, we still can pop values, we still can push values, and we're still using the stack to construct our function parameters. However, that process just looks a little bit different. So with JOP here, we can still pop values, pop another value, and push a value. Our end goal with JOP is to execute shellcode, of course, and we're going to need to deal with DEP in order to do that. So in order to defeat data execution prevention, we will use something like virtual protect in order to grant permissions to execute shellcode. And then JOP's role is setting up our parameters and calling that function to do so. At this point, I'm going to pass the presentation on over to Bramwell to introduce the JOP Rocket.
Thank you, Austin. JOP Rocket, jump-oriented programming, reversing open cyber knowledge expert tool. Yes, just by using the JOP Rocket, we are experts. And we dedicate this to the memory of Rocket Cats, who made the ultimate sacrifice. We see throughout this presentation various images of cats with a flammable device strapped to their back, and they're hell-bent on setting a castle on fire. Where this comes from is illuminated manuscripts from the 1300s that show these rocket cats trying to subvert the defenses of an otherwise very well-defended castle. With JOP Rocket, we want to do the same thing. We want to subvert. We want to provide a side door to ROP heuristics, a side door to when ROP fails, or when we just don't want to do ROP. So where did this come from? Well, it grew out of my doctoral dissertation research that I conducted, culminating in a rather large Python program, about 30,000 lines, with various dependencies, including capstone, PE file, etc. And so really the JOP Rocket is the first and only fully featured JOP gadget discovery tool. We're always adding new features. The latest and greatest is the ability to create a pre-built JOP chain to bypass DEP. It also empowers you to build your own JOP chain purely from scratch. Now, when I started this research, I thought, well, if I did a dynamic approach, if I built something to integrate with, say, WinDebug or Immunity, that would be very easy for me to do. Too easy. So I wanted to challenge myself. And so I decided, let's do static analysis. So it is able to go in there and extract the image executable as well as all the modules and get those gadgets. And when it's getting the gadgets, it's simultaneously at the same time is classifying them into categories based on operation performed, based on register affected, and literally there's hundreds of data structures used to store this information. Now, we've mentioned the pre-built JOP chains. We'll get to that later. Other new features include the ability to filter and exclude on bad characters. We don't like those, or on mitigations that we just don't care for. Now, JOP Rocket does provide significant customization when you're trying to initially form and find these gadgets, so you can reduce or enlarge the scope. And like any ROP tool that I can imagine, it also uses opcode splitting, which enables us to find the unintended instructors, because unintended instructions that are viable. That is one of the great features of x86 Intel architecture. So let's look at the JOP ROCKET command line interface. Now, the first thing we want to do is pick out the registers we're interested in. So if our functional gadget ends in jump EAX, then the rest of them will probably end in jump EAX unless we decide to transition to, say, jump EDX. So pick out the registers that you want, and then we can type G to extract those. Or if we want everything, which is probably what I would do, just do the big G. And then S, we can establish the scope. Is it the image executable, or are we getting all the modules and DLLs? And if we want to extract the modules, we'll also need to do the M, which will do that, and also get the mitigations. And then at this point, everything has been found. It's been classified, so it can now be instantaneously retrieved. And to do that, we'll go into our print submenu. So first thing we want to do, we want to use the R to specify the register of interest. And then next, we want to use the G to pick out which operations we want. Or if we want all, then we can pick all. And let's take a look here at some results. Okay, so it creates a directory called waveread, and it puts all of the different files generated, and they're saved based on operation and register affected. Let's look at one of them. Okay, this is add EBX. I have add BH. I have BX. I have add with carry. I have jump. And of course, I have call, because remember, we can also do call. So with that, I will pass it to Austin.
So we're going to be taking a look at the manual approach of JOP here, and to demonstrate that, we're going to be using a demo program, which is a simple hash cracker, and it contains a buffer overflow vulnerability. So we'll be looking at examples from that demo program and the exploit built around it in order to see some challenges associated with the manual approach of JOP. Looking at a diagram of our exploit, we have our initial buffer overflow. Once we gain control of EIP, we'll set up our registers for JOP, and we will use our JOP chain to get our parameters sorted out for virtual protect. Virtual protect will be dereferenced, the pointer will be dereferenced, and we will call that function in order to overcome DEP, and then we will execute our shellcode. Looking at our payload, we have some padding until we can control EIP. Then we have our JOP chain, which sets up virtual protect. We have our shellcode, which is a proof of concept message box, and then we have some additional padding and our dispatch table. Our dispatcher gadget is this one on the left, where we have EDI reserved for use of our dispatch table. That's the pointer. And we have add EDI 8. Since we have add EDI 8 and each pointer to gadgets are only 4 bytes, we will need to add 4 bytes of padding in between each pointer. When we gain control of EIP, we want to set up our JOP control flow, that register for our dispatcher gadget, and our dispatch table. In an ideal world, we can use a JOP setup gadget, so we are using pure JOP here. However, with JOP, we only have access to one gadget to set everything up, because we don't have our control flow set up to use multiple. So in a more ideal world, we can use a series of ROP gadgets, which do the same thing as the JOP setup gadget, however, with ROP. So this might be more practical, and finding that magic JOP gadget is not so easy. With our ROP setup gadget, we're doing the exact same thing, where we're loading an XOR key and some encoded pointers in order to overcome BadBytes, and then we're just getting that dispatcher gadget and our dispatch table pointer set up in our registers for our control flow. After that, we can return to doing JOP and just jump to our dispatcher gadget. One thing to note is that even though JOP is jump-oriented programming, we can use gadgets ending in call. The call gadgets are the same thing as a jump gadget, they just have an implicit push of the instruction pointer beforehand. So in normal x86 programming, that would allow you to return back to whatever instruction was next after you perform a function call. For our purposes, we can still use this call gadget. However, we do need to make sure that push isn't going to overwrite anything we need. And then afterwards, we can just use a pop gadget in order to repair ESP. We'll be using virtual protect in order to overcome DEP. As far as setting up our parameters for virtual protect goes, many of them do have BadBytes in them, so we can't put those in our payload, and we'll need to supply placeholders for these parameters. However, one parameter, LPF old protect, does not have BadBytes, so we're fine to supply that in the payload. The placeholders will be overwritten by JOP later. They're just there to keep track of where we are. We have two main methods of overwriting placeholders. Push is one, more realistic and more common. We will need to work with the stack, however, which is a challenge, and we only need one register for push. For move dword pointer, we don't have to work with the stack. However, we do need two registers reserved, one for the address to write to, and then one for the value. And registers are in short supply with JOP because we have two reserved for our control flow already. Looking at an example of the push method, we can get our value for our parameter that we want set up in a register, and then we pivot ESP 4 bytes above the location we want to write to, because push is going to overwrite to ESP -4. Once we perform our push, we will do our overwrite. Looking at a generalized example here of how to do push for if we wanted to do push for every single parameter, we can lay out our stack like this, where we have parameter 1, 2, then 3, which will be XORed, of course, to overcome BadBytes. And then we have placeholder 1, 2, and 3 directly after. With this layout, we can do this method where we pop our first parameter off the stack, XOR it to avoid BadBytes. Then we pivot ESP 4 bytes above our placeholder because of that ESP -4, where push is going to write to. One way to pivot is via pop gadgets, which increment ESP by 4. Once we do our overwrite with push, we pivot ESP backwards to our parameter 2 value, and then we can repeat the process with every parameter. The reason that we can use the same offsets for our pivots is because with this layout, the distance between each placeholder and each parameter is always the same. So here, parameter 1 is 0xc away from placeholder 1, and then placeholder 2 is the same distance from parameter 2, and so on. Looking at our move dereference method, once we get our gadgets, or once we get our registers set up via our gadgets, we will need to have the first dereference register being the address that we're writing to, and then our second register being the value that we're writing. So here we have EVX set up with the address, and we have ECX set up with our value, and then once we execute this gadget, we will overwrite our parameter. After setting up all of our parameters, we're going to call our API function to overcome DEP. We will need to pivot ESP to the beginning of all of those parameters to make sure we are using the correct values. There's multiple ways in order to actually dereference the pointer and make the call once we're ready. So one way is if EBX contains the virtual protect pointer, we can do jump dereference EBX. Also, we can do move EBX, dword pointer EBX, and then do a normal jump. Or we could even dereference in place like before and then jump or push to the stack and then jump to ESP, which is actually what we will do in our exploit. So looking at our demo of this exploit, we will look at immunity and see how this all works. Okay, so we're going to start out in our JOP setup gadget here. We have our pops with our XOR keys. So we have dispatcher gadget address and EDX and our dispatch tables address and EDI. We will follow that in the dump so we can see our actual dispatch table. You might notice that our setup gadget ends in a call, so we will need to pop off that implicit push that we were talking about earlier. So if we look in the code here, we can see that this first pop here is just labeled pop junk because we don't care about that address at all. We're just fixing our stack after our call messed it up a little bit. So we will do our first pop, and then our next pop will be our shellcode's address, encoded of course, which will XOR. So you can see in the code we've labeled that value will get XORed to our shellcode's address, and this address will actually be used for two different parameters, one of them being the return address, and then the next one being the LP address. So first we'll pivot ESP. After we get our XOR set up, we'll pivot ESP to our corresponding placeholder. We're actually going to overwrite the return address first, even though it's the last placeholder in order, because the pivot backwards to the next placeholder that we're going to use the same value for is easier that way. So here we'll do our overwrite. We can see in the dump we have it highlighted, and we can see that we're going to overwrite that 7070 value here, corresponding to what's highlighted in the dump in the bottom left. Once you do our push, we will have pushed our return address. And then now we'll just pivot ESP again using the same value. We don't need to change the value here because we're using the same thing for our LP address as well. So we'll do that overwrite. And then following that, we'll do 2 move dereference overwrites. So skipping the register setup for the move dereference because there's a lot of XORing, we will set up our size parameter to be written with EBX being the address to write to and ECX being the value. So we're writing that 250 value. So now we've overwritten DW size, and next we have our new protect setup. So lastly, we're going to write that new protect value. That 40 corresponds to read write execute. Now we get our virtual protect pointer because we have our parameter set up. We dereference that. We're going to push that onto the stack. After we push that onto the stack, we'll do jump dword pointer ESP to call the function. Immunity will show us that we have all of our parameters set up correctly, and assuming everything worked correctly, our shellcode should run. And we can see we did it. We got Black Hat 21 to display our message box, our proof of concept, and we've successfully performed a JOP in order to run shellcode. At this point, I'm going to pass the presentation back on over to Bramwell.
Thank you, Austin. Automated generation of JOP chains. Let's dig into it. So the manual approach that Austin described is kind of weird, kind of scary, kind of complex, a little bit ugly. But what if we could simplify JOP? What if we could make it a little bit easier to do? Dare we attempt such a thing? And I say, let's just do it. And so we've done so. And we take inspiration from a tool like Mona that can enable us to bypass DEP with return-oriented programming using APIs like Virtual Protect and Virtual Alloc. So the ideal way to set up ROP is we will take all of our parameter values for the Win API, plug it into registers, and then push add. We'll push them onto the stack in a very, very specific order, and then make the Win API call. With JOP, there is no magical push add instruction. But instead, we'll just take all of our parameter values in a very specific order, dump them onto the stack, and then use a series of multiple stack pivots to reach that location, and then dereference the Win API call, and from there, the rest is history. Now, what JOP ROCKET does is it will try to produce distinct JOP chains for each and every register, because remember, these registers are very conflicted. So we have register always tied up for the dispatch table and also tied up for the dispatcher gadget. So if we interfere with those registers, it breaks the control flow. And at the same time, if you have a functional gadget that ends in jump EAX, well, it's probably going to stay in jump EAX and not go and end in jump EBX. So there are lots of different possibilities in terms of the different JOP chains we can generate. We also produce 5 variations for each specific register utilizing different stack pivot amounts. Now, the premise behind our stack pivots is imagine that you have a buffer overflow, you have an SEH overwrite, whatever the case, and you need to do a pivot of 5,000 bytes to reach your destination, your payload. I mean, you could do that with one gadget if you found it, but at the same time, with JOP, you can also do it with many other different stack pivots that jointly can allow you to reach that destination. And then from there, we just simply make the Win API call. So let's look specifically here. So we have ESI, and we add ESI, and then dereference it. That takes us to our dispatch table. And then over here, we have 4 different stack pivots equaling about 5,000. We have our parameter values. We have the pointer to virtual protect. We plug that in over here with the pop EAX. We dereference it. And if we precisely calculate it with the right stack pivot amounts, at this point in time, it's ready. Everything is ready, and it'll work. No need for a push add. Now, specifically how the JOP ROCKET generates this is firstly, it's going to try to find the dispatcher gadget and then calculate the necessary padding to place between each functional gadget. If it doesn't find a dispatcher gadget, it'll still produce a chain because you can always enlarge the scope or look for alternative DGs. Next, it'll use two ROP gadgets to load the dispatch table in the dispatcher gadget, and then from there we start the job. It'll find your WinAPI functions and also calculate the stack pivots to match the minimum and the maximum that you specify for desired stack pivot amount. So quick and dirty method with the JOP Rocket. You can clear your current settings, go into the JOP chain menu and do the G or Z, and it does everything. Now, that's not terribly realistic because if you know you have a 900 byte stack pivot, enter that 900 and it'll calculate it precisely. That's what we want. You can also change the number of pre-built JOP chains per register. So this comes from a binary that we did at DEF CON, a very, very elaborate binary. And this is the result, auto-generated, and it pretty much works. So this is virtual alloc. And then we have virtual protect. All we need to do is just plug in the stuff for the vulnerability and then some file format issues that are not related to ROP or JOP. But the actual JOP itself does work. So let's look specifically here at virtual protect. We start with ROP. We're going to load EDX with the dispatcher gadget. And then now we are going to get our dispatch table into EDI and then call the dispatcher. We have a stack pivot of 894, another stack pivot, and then we load the pointer to virtual protect. So now we can dereference it. And then that takes us over here. Let's bundle our gadgets. And then here are our stack parameters. So we can customize these to whatever we may need. And this gives you a good starting point. And then some other stuff just that are useful generally in terms of getting your getting it built. So we have a little ROP chain, we have a JOP chain, a VP stack, etc. Let's see this in action here. This is exactly what we've just been looking at. So stack pivot of 894. We have adding C to with our dispatcher. Another stack pivot of 894. Right on back to the dispatcher, adding C to EDI, then dereferencing EDI. And now we're loading virtual protect into EAX, the pointer. Another dispatcher. Okay, so virtual protect, we see it up there. It's about to make that call. And over here, we have, look at ESP, we have a stack parameters set up, and we got it. And the Rocket Cat got our shell code. Now, that's ideal. The reality, though, is sometimes you have to tweak your job. But at the very least, JOP Rocket provides an excellent starting point. Ideal requirements. Well, of course, we need a dispatcher gadget for this to work. Next, ideally, we would have no BadBytes. However, we can still work with BadBytes if the gadget addresses do not contain them, or even still, if they do, BadBytes is not the end of the world because we can always change the BadBytes to something else. One way around them is with this method. So let's say CD is a BadByte. Well, let's do the unassemble inside JOP Rocket, and now I'll have CA. That may not always work. So a better approach is exclusive OR. So if we have 7 XOR 5, well, that gives us 2. And we can take that 2 XOR 5 right on back to 7. And we have dead code and decode and gives us 400,000, the image base, and we have our no bytes over there. JOP Rocket also gives you the functionality to simply exclude BadBytes. However, I don't recommend this because we can always just simply transform the BadBytes with exclusive OR. So if there are BadBytes, you can still do the generated chain. You just simply may supply dummy variable values instead, and then you can go and overwrite them. One way to do that is by sniping with the move dereference, and that is extremely effective with ROP or JOP. However, with JOP, that gadget is relatively rare. So another way to do that, and this is unique only to JOP, is push instruction, which Austin explained, and this is also a technique that he created. So let's look here at the move dereference. We load an XOR value, we have the XOR key, and then we do a transformation, we overwrite it, and then we increment, and then we can repeat as many times as we need to in order to overwrite all of the dummy variables. Of course, JOP Rocket is going to deliver for us. It'll find those move dereferences if they are there to be found. If they're not, remember, we can always do the push method instead. So with that, we will pass it on over to Austin.
So first on our list of topics here, we have switching registers for your functional and dispatcher gadgets. So one reason we might want to switch registers for your dispatch gadget is because if we have our gadgets ending in jump EDX, with the EDX storing our dispatcher gadget, but we have another gadget which we may want to use that ends in a jump EBX, that EBX gadget is off limits currently because EBX will not bring us back around to our dispatcher gadget. So in order to fix this, we can perform a pop EBX, popping that dispatcher gadget's address into EBX, and now once we perform jump EBX, we will return to our dispatcher gadget, allowing us to use that, that previously unavailable gadget. In a similar vein, when we pop a dispatcher gadget into EBX, we can also switch dispatcher gadgets entirely. So the reason to do this, if we look in our gadget in the top right, we have add EDI 8, jump dword pointer EDI. So EDI is being reserved currently for our dispatch table. With our new dispatcher gadget, we're using EBP for our dispatch table instead. So now we can use gadgets that will modify EDI without ruining our control flow. So here at the bottom, we have our example where we pop EBX with an alternate dispatcher gadget, and then we can do our add EDI gadget without ruining our control flow. Switching gears here, we're going to talk about Microsoft's Control Flow Guard, which is a coarse-grained CFI implementation which inserts check functions before indirect jumps and calls. This is going to attempt to thwart exploits similar to JOP. We do have some techniques to avoid Control Flow Guard. One such technique is opcode splitting. So for an example of that, at the bottom here, we can see our first instruction starts with the opcodes BF89. However, if we strip off that BF opcode, we get a different instruction, which is actually a JOP gadget. And this is an instance of an unintended instruction. However, it's still valid in x86 assembly, and we can use this as a JOP function, as a JOP gadget, without worrying about Control Flow Guard. We have some other ways to avoid Control Flow Guard. So indirect calls occurring during inline assembly are not going to have that check function inserted before them. We can also avoid CFG by using gadgets found in DLLs which don't have that CFG protection enabled, and Windows 7 doesn't support CFG either, so when running exploits on Windows 7, we don't have to worry about that. The JOP Rocket will allow us to enumerate whether or not modules have CFG enabled, and we can also filter out gadgets from CFG-enabled modules. However, I don't recommend that you filter out those gadgets because many JOP gadgets can occur from unintended instructions via opcode splitting like we were talking before, and as long as you don't execute that guard check function, we can use our JOP gadget. At this point, I'm going to pass the presentation back on over to Bramwell for one last time.
Thank you, Austin. Our next technique is bypassing ASLR with JOP. And let me level with you. It's no different than doing it with ROP. So imagine that you have a memory disclosure with a UAF. You have an integer budget as part of a structure. It displays the budget. You free the structure, and then you go and try to display the budget again. This is called a use after free. You're using it after it has been freed. And it's going to display nonsense, nothing useful. Well, we can instead go and overwrite that allocation with a similarly sized structure. And instead of an integer at the first offset, well, maybe we'll have a function address. And thus, instead of displaying a random integer or nonsense, we are leaking a function pointer. And from that, we can go and extrapolate the base address of the DLL. And this is the ASLR bypass that we want. If you do this, you've bypassed ASLR. Another technique that we can use is using JOP as ROP. So if you're doing return-oriented programming and you can't find the right ROP gadget that you want, one thing that you can do is briefly transition to JOP if you can find the equivalent JOP gadget that you want. How you do that is you go and load a return instruction, and that's it, just ret, load that into a register, and then when you go and jump to the register, it is then equivalent to a ROP gadget. And you don't need to mess around with a dispatcher gadget or a dispatch table. You can just briefly do JOP and then return to your other ROP. Now, one recent innovation that we provided is expanding the definition of what constitutes a dispatcher gadget. With ROP, you look for the C3 opcode and disassemble backwards. So we do the same thing with JOP, looking for particular offsets, but we found that we're missing the opcodes for if you do a jump D-word pointer plus or minus an offset, because this is a valid way to do it. So we've added those opcodes, and we've added this and other alternative forms of the dispatcher gadget that you can also read about in the white paper. You know, ASLR and DEP, they're strong mitigations, but we can overcome them with JOP just the same as we can with ROP. The only challenge is that with JOP, the gadgets are a lot less plentiful, so that could be a possible consideration if there are not enough gadgets. Some final takeaways. If you can find a dispatcher gadget, don't be afraid to try JOP. It may actually even be easier. And if you are doing just exclusively ROP, but you need a specific gadget, well, you can briefly transition to JOP and expand your attack surface. If you want to try the pure JOP style, we have a couple binaries you can try. We have an easier and a slightly harder, and you can find those at the GitHub or joprocket.com. And with that, we welcome any and all questions.